Welcome friends, Igor is here, and in this video we will talk about definition and examples of vector spaces. In this lesson we will define the notion of a vector space structure and we will discover some simple examples of vector spaces. Let's get started. So far we worked only with explicit objects in this course, such as, for example, column vectors and matrices. Having these explicit objects, we explicitly defined operations with these objects. For example, we defined how to add column vectors and matrices, and we defined how to scalar multiply column vectors. These operations were defined explicitly given the objects at hand. But then we discovered that these operations defined on different objects satisfied the list of 10 identical properties. So the question is, how many times do we have to do it? What if we encounter a third type of objects? We define again operations on that objects only to later discover that these operations still satisfy the same 10 properties. Why not instead adopt an abstract approach? We will define a certain structure by only saying which properties this structure satisfies. Of course, this structure will be motivated by known instances of this structure. In this case, it's column vectors and matrices. But the advantage of this abstraction, of this generalization, is that whatever you prove about this general structure can be applied automatically to all instances of this structure. So instead of proving that this and this property holds for the column vectors and also this and this property holds for matrices and this property holds for another example of this structure, you prove it once in general and then it will automatically transfer to all instances of this structure. This is the power of mathematical abstraction. And now I want to congratulate you because we have come to the most important definition in linear algebra. This is the definition of a vector space structure. This structure consists of several ingredients. First of all, you have to have a non-empty set of objects. In addition to this, you need two operations. One operation we call vector addition, another operation we call scalar multiplication. The operation of vector addition combines two elements of a given set to produce another element of the given set, and the operation of scalar multiplication combines a number with a given element of a set to produce another element of the set. This structure, which comprises a set V plus the two operations, is a vector space if the following 10 properties hold. This is exactly the same 10 properties that are satisfied by the operations of vector addition and scalar multiplication for column vectors as well as for matrices. The elements in the set V are called vectors if V with the given two operation forms the structure of the vector space. So if you ever wondered what is the definition of a vector, what a vector really is, then the rigorous mathematical definition is this: a vector is simply an element of a vector space. Now, let's discover some simple examples of vector spaces. And the first example is the vector space of column vectors. So we fix a dimension m and we look at all column vectors of size m. Then the operation of addition on this set is our usual operation of addition of column vectors, and the operation of scalar multiplication is the usual operation of scalar multiplication of column vectors as we know it. Does this structure form a vector space? The answer is yes, because we already know that column vectors with respect to the given two operations do satisfy the list of these 10 properties. Therefore, column vectors of a fixed size with these two operations are an example of a vector space structure. Next example is the set of matrices of fixed size. We consider all possible matrices of size m by n with entries from the set of complex numbers. We take the usual operation of addition of matrices and the usual operation of scalar multiplication of matrices which we defined earlier. Does this structure form a vector space? The answer is yes, because we already proved earlier that matrix operations do satisfy all these 10 properties. Therefore, the set of all matrices of size m by n with these two specific operations is an example of a vector space structure. Let's fix a natural number n, and we are going to consider the set of all possible polynomials of degree at most n. These are polynomials in one single variable, let's say x, and the coefficients of these polynomials could be complex numbers. We will define the operation of vector addition on this set in a more or less natural fashion. We will add the polynomials as if we were adding them as polynomial functions. Also, we will define the operation of scalar multiplication in the following way. To scale a polynomial by scalar alpha, you just multiply every coefficient by this scalar alpha. Again, this is what we would have done if we treated these polynomials as polynomial functions. Now, please, as an exercise, check that this is an example of a vector space structure. Please check that all 10 properties of the operations do hold in this case. In the next example, our set is infinite sequences. We define the operation of addition on infinite sequences in a natural way. We simply add them component-wise. Also, we define the operation of scalar multiplication by scaling every component of an infinite sequence. Again, please check carefully that all 10 properties of the vector space structure hold in this case, and therefore this is yet another instance of a vector space. Next, let me construct a vector space structure out of functions. The underlying set is the set of all possible functions from, say, complex numbers to complex numbers. We define the operation of vector addition on this set as you would normally add functions in, say, calculus. So the new function f plus g has a property that its value at point x is the value of f at the point x plus the value of g at the point x. Notice in this equality, the plus sign on the left-hand side is the new operation we are defining. This is the operation of addition of functions. On the right-hand side, this is the operation of addition of numbers, because we are adding values of functions at a given point x. We can also define the operation of scalar multiplication on the set of these functions in a natural way, like you would scalar multiply a function in calculus. The value of the new function alpha f at the point x is the value of the function f at the point x multiplied by the scalar alpha. Again, please check that all 10 properties of vector spaces hold in this case, and therefore this is yet another instance of a vector space structure. In this case, vectors are actually functions. Could you imagine, before you saw this example, that functions can be actually vectors? For the last simple example, we will consider the so-called singleton vector space. The underlying set contains only one single element, which we call z. Then we define the operation of vector addition. Well, there is not much choice in this case. There is only one vector, so z plus z, what could it possibly be? It has to be back in your set, so you set it equal to z. Also, if you scalar multiply any vector, there is only one element z. Any scalar multiple is just the element itself, because you do not have any other choice. Well, this certainly looks weird. What is z? What kind of an object is it? Is it a vector, a matrix, a polynomial, or a function from before? Well, it doesn't matter. Just think of this as some object which you call z. For example, in this case, this object z is the zero vector, which every vector space must have. Also, the negative of z is z itself. Please check it. also check that in fact all 10 properties of vector space hold in this trivial case. So this is an example of a vector space. It contains only one single vector, and of course this one single vector is the zero vector in this vector space. Now, you may complain that I gave you too many exercises. I asked you to check yourselves that certain structures satisfy the vector space properties, and you might say, well, how do we do this? We don't know how to do this. Well, we will handle this in the next video, where I will work out a much more complicated example than I gave here, and I will walk you step by step through all the 10 properties of the vector space. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, I will teach you how to check all 10 vector space properties one at a time, carefully and methodically. I will see you later.